Thank you for attending the talk. This is the last talk for this session, and I also think this is the last talk for this year's KDD conference. So thank you for staying here. The topic is human mobility synchronization and tree purpose detection with mixture of Hawkins process. So we can see there are two keywords. One is synchronization, and the other is tree purpose. So actually, synchronization is a very common phenomenon in the nature and also in human world. Just now, we have experienced some synchronization in this conference hall with the applauds. Somebody start to applaud, and others follow, and then this person stop to applaud, and others also stop. That is a phenomenon of synchronization. And similar phenomena is also witnessed in opinion formation. For example, there is a opinion leader, he proposed something, and the group members exchange their ideas, and finally they reach agreement. This is another case for synchronization. But how about the synchronization in our human mobility? We observed an interesting phenomenon. That is the taxi arrivals for different airports in New York City. One is JFK Airport, another is Newark Airport. Both of them are very busy international airports. And once we see the arrival rate at a different time period of day, we see the histogram is pretty similar. For example, for both of the airports, the peaks appear at about 6 to 8 in the morning and also in the afternoon. So we'd like to say, we want to explore what actually drives the mobility synchronization. As we can see on the map, the two airports are quite distant away. But why they show similar arrival patterns? So we want to ask why people go to airport. I think the answer is pretty obvious. They go to pick up somebody or just to fly out. So this is just their trip purpose. And this trip purpose is determined by the time of the flights, the schedule of their flights, and this determines their arrival patterns. That is when they go to airport. So we can see from the distributions of the two airports, and that drives the human mobility synchronization. So we have trip purpose, we have synchronization, and then we have to link the arrivals, regions, and purpose together to discover the underlying trip purposes and the human mobility synchronization across different regions. Here is another example, and this is also our framework for our work. We can only observe the arrival sequences at different regions in the city. Still take New York City as an example. We see Times Square and also Wall Street, and we witness the arrival patterns for the different regions, and they are actually we can only observe the arrival sequences, and they actually are homogeneous. But underlying the homogeneous arrival sequences is different trip purposes. For Times Square, it is a multiple functional areas where people can work there because they are office buildings. And it is also a famous sightseeing places. All the travelers go there would go to visit Times Square. And similar things happen for Wall Street. So we can see the trip purposes for the two places are pretty similar, and which can result that their arrival patterns be similar. But we also, given these arrival sequences, the next step is to discover the semantic millions for their trajectories. What we observe, we actually observe the geographical environment of the origins and destinations. For example, for Times Square, just as I have mentioned, there are some office buildings, there are some restaurants, and also some sightseeing places, and they are mixture of functions. And this mixture of functions is also similar for Wall Street. And then we trace back the origin places, whether they come from their residential areas or from some hotels or just from airports. This point of interest information gives us the inspiration to explore the tree purposes underlying these arrival patterns. So our problem here is to bridge the arrival sequences with the latent tree purposes. Our model is composed of different building blocks. Firstly, we have to model the arrival sequences. For each region, we organize the taxi trajectories as a sequence of arrival events, which is denoted by E. And this E is not only composed of the time, but also the point of interest of the origins and destinations, which is denoted by W. So each event is composed of a 3-element tuple, and we try to recover the sequences from a statistical process. And we see that the historical arrival events may have great influences on future events. So we have to model a single pattern of arrival sequence by a Hawkes process. This Hawkes process is just formulated as a lambda t, which is the arrival rate at time t. It is composed of 2 parts. One is mu t, which is just the base rate for arriving at this place. And another building blocks is the influence from the historical events. We use a kernel function to denote the time decaying effect and to show the self-exciting property. And this self-exciting property is just a property for Hawkes process. And it also corresponds to our intuitions that the historical events at place can have a great influence on the future events. This is on this map, on this time axis, we only model one purpose, but actually we have multiple tree purposes. For example, for Times Square, we have eat, working, relax purpose, and it is denoted with different colors, purple, red, and blue. And these different colors of arrival patterns, just when we mix them together, and we can get when we mix them together, we can witness the arrival patterns. And then, as I have said, there are different tree purposes, and when we mix the tree purposes together, we propose a mixture of Hawkes process, which is actually the base lambda I with different tree purposes, lambda I and m. This m is just the latent tree purposes. This lambda is also composed of 2 parts. One is the base rate for the tree purpose with m that arrive at I, and then it also composed of a decaying effect from the historical events, which is denoted as a kernel function g. With these tree purposes, the arrival patterns or the arrival rates for a particular region I can be viewed as a summation of different tree purposes. Like, for example, the lambda IT can be a summation of lambda I of eating purposes, and the lambda IT with working purposes, and also with different purposes. And the arrival patterns can be viewed as a mixture of these purposes. So with the mixture of Hawkes process, we have modeled the arrival sequences. But as in the first slide, we talk about the synchronization. So where can we encode the synchronization in this arrival rate? Here we use row networks, which is in analogy to a graph. Different nodes or different regions, different nodes represent different regions, and the regions are connected by edges. And the weight on the edges can be viewed as a synchronization rate between different regions. With this analogy, for example, for region I, it can be synchronized from some neighborhood nodes like region J and some other adjacent nodes like region K or region L. And all these arrival patterns can be synchronized to region I with this alpha rate. And also to notice that the alpha rate is tree-purpose dependent, which is actually a three-dimensional matrix with J's influence on I with tree-purpose M. So with this synchronization rate, we can enhance the mixture of Hawkins process with the synchronization rate on the arrival rate. Still, we have the base rate for tree-purpose M arrive at I, and also the decaying function from historical events. But we have some neighborhood environment or some synchronization events that can be synchronized to this particular place. And we just use alpha Ji M to encode these factors. With these equations, we can both encode the self-exciting property within a region and also the mutual exciting effect across multiple regions. So this lambda help us deal with the tree purposes arrival rate, the arrival rate with different tree purposes. Then we have already modeled the arrival sequences, but next step is to give some semantical meanings. Where does the semantical meanings come from? That is from the POI, point of interest information from the origins and destinations. For example, for the working purpose, you usually start from residential areas where are some residential houses, and the destination may be full of different office buildings like in Wall Street or Times Square. And we use an analogy from topic model. We regard a region, the point of interest in a region as a document. And each point of interest can be regarded as a word. And the tree purpose is then semantically embedded in the neighborhood POIs of both origins and destinations. And the neighborhood POIs can be modeled as a mixture of latent, or we call it POI topics. So we generate the POI of the origins and destinations respectively from the latent tree purpose. We firstly generate a latent tree purpose from a multinomial distribution. And for the origin place, we generate the POI topic ZO. And for the POI topic of the origin of the destination, we draw a latent topic ZD. And then is similar with some with topic model, and we draw the particular POIs from the neighborhood. Then here comes our joint mixture of Hawkins process. We not only model the arrival sequences, we also model the POIs with a topic model fashion. So that is a joint model between Hawkins process and also extended topic model. To infer the parameters from the topic model, from this model, we use variational inference, where we use an auxiliary distribution for latent tree purpose and also the latent POI topic. With this Q distributions, we can get the evidence lower bound objective function for this likelihood function. And then we can derive the parameters in the models. One is tree-purpose distribution. As we can see from the very complex equations, it can be decomposed as different parts. One is the influences from the past, and the other is the influence to the future. And also, the influence by the tree purpose and some the related point of interest are also embedded in the inferred tree purposes. And also, we can infer the POI topic for different regions, and then we update the parameters. And finally is the experiments. Actually, we don't have the ground truth label for each trip purpose. We don't know. We don't know the trip is actually for working or for homing or for recreation. But so here we can only use synthetic data. Synthetic data is generated with the Ogata's modified thinning algorithm. We use this algorithm to sample the arrival sequences, and also we use the generative process of a topic model to generate the neighborhood POIs. The task of this experiment is to cluster the trajectory based on the inferred trip purposes. We see whether our model accurately identify the trip purposes or cluster different trajectories into different clusters. We compare our method with the original mixture of Hawkins process and also LDA, latent derisoly allocation, and also clustering method like K-means. We use some clustering validation measures to validate our performances, including purity, FM measure, and rand statistics. And as shown in the figure, our joint mixture of Hawkins process outperforms other baseline methods in terms of different metrics. It shows that this model accurately or in a more accurate way to cluster different trip trajectories. And also validate our model on real-world data. The real data is from New York City's taxi trips, which is sampled from 7-day taxi trips. And we also do some data pre-processing and obtain 152 valley regions. And we use the Google map for the point of interest of NYC. Here, the table shows the identified POI topics. As we can see, each POI topic accurately clusters some different POIs with some semantic meanings. For example, in topic 1, we see bars, nightclubs, event space, which can be inferred as the nightlife topics. And also some topics are about dining and also on working. And also topic 10, we can see home building, some laundromat, which can be inferred as a home. Also, some POI topics are a little bit ambiguous. We also check the POI topic distribution over latent trip purposes of the origin and destinations with this heat map. For example, for trip purpose 5, we can see on the drop-off point, that is the destination point, it has a high value for topic 10, which is denoted by home. So this trip purpose can be semantically explained as a go back to home from different places. We also use a case to illustrate, to validate the synchronization effect, whether synchronization effect exists in our model to show different places if our model have a higher synchronization rate, whether they will show similar arrival patterns. For example, we choose A, B, and C, 3 different regions, and calculate the synchronization rate from our model. And we can see for A and B, the synchronization rate is greater than that of A and C. And then we check the arrival pattern for these different places. We can say A and B are quite similar in terms of the arrival patterns. And A and C and B and C are different from each other. And finally, our concluding remarks. We study the problem of human mobility modeling, and we try to tackle 2 research questions. One is, what is the nature of human mobility synchronization across functional regions? And also how to spot and trace the trip purposes of trajectories. We try to model, from the model perspective, we provide a unique perspective of modeling human mobility as statistics point process. And we also use human mobility synchronization property to link the arrivals, the regions, and the trip purpose together. So that is the end of the talk. Thank you.